about the design of a PMOS MOSFET. By design, it means that you need to find the biasing resistors R1 and R2, and what you are given is your IDQ, that is the DC current at where the transistor is biased. So you have the Q point, okay. So and similarly, you have this VSD. This is your source. This is your drain, and this voltage in between is VSD. Now, as you can see from the symbol of MOSFET device, this is a PMOS device. Okay, so the direction of current is into the source. Okay, so so you need to find this biasing resistors. Okay, which ensure the given Q point is as such that IDQ is 100 microamps and VSDQ is 3 volts, and this VSDQ is going to determine whether the transistor is in sat region or it is in unsat region. Okay, so we have to determine this whether it is sat or unsat. I mean, non-sat region. So the other thing is that you need to find RD as well. Okay, which is your the resistance at the drain. Okay, and you're also given VRS 0.8 volts. This VRS is 0.8 volts over here, right? And this we'll see later on in this example. This resistance is the importance of this resistance. What it does is it helps in stabilizing the bias or stabilizing the Q point of the transistor, given the variation in the transistor parameters like Kp. The Q points doesn't vary much. That is, the current and the voltage variation is small. Okay, even if the transistor parameters are variable. So note that VRS is a voltage across the source resistance. Okay, in the previous example of NMOS, we didn't consider any source resistance over here. So now we have this source resistance. So the value of the larger bias resistor, either R1 and R2, is to be set to 200K. Okay, so whichever is larger of R1 and R2, the biasing resistors. So the maximum of R1 and R2 is to be set equal to 200K. Okay, so maximum of whichever is the maximum, we're going to determine. So for the determination of which is greater, we have to determine the bias current that flows over here. So this is to be set to 200K. That's another constant. Okay, one of them is to be set to 200 kilo ohms. So we are given the Q point I, V, VSD. We are given VRS. Okay, and then furthermore, the transistor with the nominal parameters of Kp. We are given the conduction parameter. We are given the threshold voltage. Okay, note that this is negative. Why it's negative? Because we are dealing with a PMOS device. Okay, this is a PMOS design example. So for NMOS, it's the other way around. For NMOS, the threshold voltage VDN is positive because the gate voltage is positive. Over here, the gate voltage is negative. So you need a negative gate voltage to enhance or to establish an invariant layer. So threshold voltage for PMOS devices is negative. Now the conduction parameter, it may vary by plus minus 5%. Okay. Now given this variation, you will see that your variation in the Q point, that is IDQ and VSDQ, is not much if you employ a respectable resistance at the source. Okay, RS. So RS helps in stabilizing the Q point. So the objective is to design a circuit with p-channel MOSFET that is biased with both negative and positive supplies, which you can see over here. Okay, so you have a positive supply at the source. In PMOS, source is at a higher potential than a drain. Okay, so drain terminal is kept at negative potential, and that contains the resistor RS to meet a set of the specifications. So these are the specifications. So let's go ahead with the design. So the first thing you want to do is well, you have to use a current to voltage relationship, and assuming that first, let's assume that the transistor is biased in the saturation region. So we use the current to voltage relationship for the saturation region, and well, we are given with what Kp is. The transistor parameter of threshold voltage is given. IDQ is where the transistor is biased. So what is your VSG required to have a bias current IDQ equal to 100 microamps? In order to find that out, you see over here, you have 100 microamps of IDQ, and your Kp is also 100 microamps volt square. So you reformulate this equation to make VST the subject. So well, this is IDQ over KP square root minus VTP. So this minus minus becomes plus, and then you find the VSG from this relationship as 1.4 volts. Okay, so VSG over here is 1.4 volts, and this 1.4 volts is responsible for IDQ equal to 100 microamps. Okay, so for the given threshold, for the given KP, VSG is should be 1.4, such that you have your correct Q point current, which is 100 microamps in this example. Okay, that is what is desired. All right, now the other thing to note this, well, we assume that the transistor in saturation region. So if this assumption is correct, you need to check that if VSTQ, which is given as 3 volts over here, this VSTQ is 3 volts. All right. So is this greater than VST sat? Well, if it is so, then yes, the equation of current is correct. If not, then you have to revert back. You have to use another relationship for the non-sat. Okay, so we have seen this a more complicated form of the non-sat region current voltage characteristics. So there was a table. Okay, table 1. It summarized the MOSFET voltage relationships in PMOS. You see, this is your saturation. We have used this current voltage relationship. If this VSD sat, so our VSD, if VSD was less than VSD sat, well, then you have to use the non-static current equation. Okay, so this is a little bit more complicated and lengthy. But anyways, let's find out if it is in saturation or it is non-sat. What we have done over here, we have used the saturation current equation. So well, this VSD sat is given as VST plus VTP, and this is 1 volt. Okay, so your VSD sat is 1 volts. But given the Q point, the transistor is biased at 3 volts, which means you have passed beyond the saturation point, the transition point on the IV characteristic. So you're somewhere here. Okay, so this, for example, this is the transition point between the SAT and non-SAT. For any given VSG over here, this is any given VSG for PMOS, then you have VSD over here. Similarly, you have the drain current on the vertical axis. So this point differentiates okay, this point over here is differentiating between SAT and non-SAT. So you are this point is 1 volts. Okay, you are somewhere here, 3 volts. So VSD, you're already in the SAT region. So the purpose of validating this point was that this current equation, using this assumption, our current equation was correct. Okay, so we have a correct value of, as a consequence of that, we have a correct value of VSG, that is 1.4 volts. So so yes, the transistor is indeed biased in the saturation region. Now let's use this VSG in equation over here. This is KVL to find what the gate voltage is. You see, you can find the gate voltage over here. You have V positive. Okay, then you apply the KVL in this loop, V positive minus VRS, and then this is your SG. You have VSG. All right, we have determined VSG from the current equation, ID and VDS current equation, and then you're left with VG over here. Okay, so this VG is across R2. All right. So you see, if you apply the KVL from the positive supply, we have V positive minus VRS minus VSG. This is determined from the current equation, current voltage relation. Then this V positive is 2.5 volts over here, right? VRS is given as 0.8 volts, 0.8 volts. So 2.5 minus VRS is 0.8 volts, and minus VSG, this S and G, the voltage that exists. This is going to leave you with the gate voltage. Okay, 2.5 minus 0.8, 0.8 is given, 2.5 is the positive supply, 0.8 is VRS, and then VSG that we have found out is this one. Okay, so we are using this over here to determine what the gate voltage is, and that's 0.3 volts. Now this 0.3 volts is greater than 0. That implies that this R2 will be the larger of these two bias resistors. Okay, I mean there will be, if it is it's large and for the same bias current, there will be more drop over here. Okay, so you can determine that for given VG greater than 0, R2 is the larger of the R1 and R2 resistance. R1 and R2 are your biasing resistor. So whichever is larger, let's set this to 200 kilo ohms. That was another requirement. So the specification was as such that the value of the larger biasing, either R1 or R2, is set to be 200K. So we set R2 to 200K over here. Okay, it's 200K over here. So the current through R2, now we have this VG. Okay, so we have this VG. So over here, you can by Ohm's law, you can find what the bias current is, that is going through this resistance R2. Basically, this current is the same that goes through the biasing circuit R1 and R2. So this current can be found out from VG. So VG minus V negative, that is minus 2.5 volts, divided by R2, which is set to 200K, is going to give you I bias. Okay, why we need I bias? Well, that's going to give you the value of the other resistor as R1. Okay, it's the same current. It's the same current that is flowing in the biasing circuit. All right. Okay, so you find I bias VG is 0.3 as we have determined over here. Then negative supply is minus 2.5. This gives you 0.014 milliamps. Use the same current over here to find the R1. R1 is, you look at the positive supply over here. So take the difference of the positive, V positive. So that will be V positive minus VG. Okay, V positive minus VG over R1. R1 is your I bias, and you know what I bias is. Okay, you know what V positive is, you know what VG is. So all you need to do is to determine your R1. That can be done, and if you do so, you find out that R1 is 157 kilo ohms for the same bias current. So the source resistor is found from VRS. We have DRS as in the specifications, that was 0.8 volts. Okay, we have IDQ. Okay, that is flowing through this source and drain resistors. So we can find the both resistances. So VRS is 0.8 volt divided by IDQ over here. This RS is 8 kilo ohms, and so similarly the same things go over here. You see for RD, if you need to evaluate RD, same IDQ is in the drain resistance 0.1. All you need to do is you need to find VD before you find RD. Okay, because this is over here. You need this voltage is VD. Okay, this voltage is V negative. So take the difference, divide by RD is your IDQ current over here. Okay, this is your IDQ current that is flowing through the resistor RD. So okay, how to find VD is to use the KVL at the output loop of the transistor. You see over here how you determine your from the output loop is you have V plus, then you have minus VRS. Okay, that's the voltage drop across the source resistance, and then you subtract VST, that is your where the transistor is biased. Okay, VST is given as 3 volt. Okay, and then minus this, then minus VD. This should be equal to your V negative. Okay, so over here you see VD again is 2.5 minus 0.8 minus 0.3. Sorry, it's not V negative. That's 0. Okay, I mean we are over here. So V 2.5 minus VRS minus VST is VD. Actually, it's VD, or you can bring the VD to another side. Over here, it's plus VD. So this is the KVL at the output loop of the transistor over here. Okay, so V positive minus VRS minus VSD is going to give you basically VD. So yeah, so V positive is 2.5 volts, then VRS is 0.8 volts, VSD is we have determined VSD before. It's not determined actually, it's already given. This is the Q, VSD Q. So that's already 3 volts. Okay, and what you get is minus 1.3 volts as VD. Then you use this VD to determine RD. Okay, and you find this as 12 kilo ohms for the same IDQ. And well, everything is known now, fine. So whichever resistance was higher, well, we select R2 as the higher and we set it to 200 Ks, and we determine what the source and the drain resistances are, which are giving you the Q-stand value of the current at 100 microamps and VSTQ as 3 volts. Okay, and we have for the given VRS of 0.8 volts. So we've pretty much satisfied the specifications. So that was the objective. Now the choices. And the choices are as such: the transistor was given with these nominal values of conduction parameters and the threshold voltage. Now it says that if the it also says that conduction parameter may also vary by plus minus 5%. So let's see what is the effect of this variation on conduction parameter. To start with, conduction parameter variation of conduction parameter is going to change IDQ. Okay, and if IDQ was set, well, we will have a change in VSG. So let's find out how much change that it creates in VSG, and in return how much change we get in VSTQ. Okay, because we are using VST over here as well. So there will be a change in your IDQ. Okay, if for example, if you are going to set the same VST, KP is varying. Okay, so there will be a change in IDQ, there will be a change in VSTQ, there will be a change in VST. So these three parameters are going to vary because of KP. Okay, over here. So if KP over here is, you see there is a plus minus 5% variation. So from 100 microamps, there's a variation of, so you have minus 5 plus 5% variation. And this gives you VSGQ variation, first of all, as 1.416, 1.385, and if you recall, the VSGQ was 1.4, about 1.4. We evaluated this, yeah, over here. So this is 1.4 for the given IDQ of 100 microamps. And for this variation of VSGQ, if you're going to plug this in IDQ relationship, okay, over here, if you're going to plug this over here, there will be a change in IDQ. Okay, so let's see how much that is. We have the change as about 2% from 100 microamps to 98, so minus 2% plus 2%, about 102 microamps. And similarly for VSTQ, we have the variations as about 1.3%. This variation is 2%. VSTQ varies from 1.14%. So these deviations are still less than the 5% deviation which the conduction parameter had in the transistor that is available. So the quiescent drain current IDQ and the source drain voltage it does changes, yes, but it doesn't changes by 5%. It's still less than that. So using the resistor values found in the previous design, we found the following. Okay, so these variations are not much of a significant deviation from the specifications. So you note that the variation in the Q point values are small. They are smaller than the variation in Kp. So including the source resistance RT, it tends to stabilize the Q point. That's the important point over here. You recall that in NMOS example, we didn't consider RS, but over here in PMOS example, we have this RS, and the importance of RS is that it helps stabilizing this Q point. Okay, so your biasing is stabilized by RS. If you have RS, even if Kp varies, there's not much variation in your IDQ and VSDQ Q point.